Alright, so we're looking at finishing example 3. I'd like you to actually take part D and do that one yourself, because when you have a polynomial, x to the fourth minus 4x cubed, that's continuous and differentiable. That one is a very straightforward one. So I would like you to take a moment and determine the intervals where it is concave up and concave down and the possible points of inflection on your own. So pause the video right now and come back when you're ready to check your answer. All right, so the answer for this one, our first derivative, 4x cubed minus 12x squared, our second derivative, 12x squared minus 12x, our second derivative equals 0 after we factor at 0 and 1. So we do a sign chart. We put in our possible points of inflection, so that gives us 0, 1. Fill in your sign chart, make your conclusion, and then make sure you answer the question, because remember that the AP readers will not interpret your sign chart. They want you to actually answer the question. However, I'm not going to box it because we don't like to box things in. We like to get credit for everything we've written down. All right, so that one should have been very straightforward. Polynomials, you should cheer when you get a polynomial because it is usually the most straightforward concavity test to do. All right, so now let's take a look at the second question. Now this one is a little bit harder because you're going to have some chain rule involved, and then once you get the first derivative, you'll see that you're going to need a product rule. So let's go ahead and do the first derivative. And I will make a note that y is continuous and differentiable, that we have the composition of two continuous differentiable functions. And our first derivative would be derivative of e to anything is e to that stuff times the derivative of the stuff, which is going to be negative 2x. And I'm just going to write that in a nicer form so that I can get ready to use the product rule. So as soon as you see that you have negative 2x times this e, you're going to have to use your product rule to find the derivative. So now we'll go to our second derivative, which is going to be the negative 2x times the derivative of e to the negative x squared, which we just did, negative 2x e to the negative x squared, plus my e to the negative x squared times the derivative of negative 2x, which is negative 2. We will factor this to get it into a nicer form. I'm going to pull out a negative 2e to the negative x squared. Here I'm going to be left with negative 2x squared, and then over here I took both of them away, so plus 1. So our possible points of inflection are going to occur when the second derivative is 0. And that's going to occur, notice I don't have to worry about this factor, because this factor, e is never negative or 0 when you do e to a power, so I don't have to worry about it. So that's only going to occur when negative 2x squared plus 1 is 0, or x squared equals 1/2, x equals plus or minus 1 over square root of 2. So we'll set up our sign chart for our second derivative for our concavity test. We'll put our possible points of inflection on here. Okay, we'll do our test. E to anything is always positive. If I plug in, say, negative 10 here, this is going to end up being a negative number times a negative number, or positive. If I pick 10, this is going to be a negative number times a negative number, which is positive. And if I pick something like 0, we would end up with a positive times a negative, so it's negative in the middle. So we can conclude that the original function y is concave up, concave down, and then concave up. And since it was continuous and differentiable, then we know that y has a point at negative 1 over square root of 2 and 1 over square root of 2, and y has a tangent line at negative 1 over square root of 2 and 1 over square root of 2. So we can answer our question that f is concave up for negative infinity to negative 1 over square root of 2 and 1 over square root of 2 to infinity, because f double prime, let me use y because I've got to use the labels that they gave me. Y is concave up because y double prime is greater than 0. Y is concave down for negative 1 over square root of 2 to 1 over square root of 2. And there are points of inflection at x equal to plus or minus 1 over square root of 2 because y was differentiable and continuous, and the second derivative, y double prime, switched signs. Notice I got away without having to say that y existed there and y prime existed there, because that's what it means when I say differentiable and continuous. All right, and I think I forgot over here, because this was a polynomial, I should, in this first one, I didn't put that answer, hopefully you did when you did the problem. We should also say that x equal to 0 and 1 are points of inflection. Locations of points of inflection, because f was continuous and differentiable, and f double prime switched signs. So I forgot that we were doing points of inflection as well. All right, so let's come over to the next example, a fun one. You think, oh yeah, that'll be easy, right? It's a continuous and differentiable function. Our g prime of x is equal to 4x cubed, easy. G double prime of x is 12x squared, again, easy. Our second derivative equals 0 when x equals 0. So there's our possible point of inflection. So we come across, we put our critical value, we do our sign chart for our concavity test, and then we test. If I plug into any number into the second derivative, notice that it's 12x squared, so it's going to be positive and positive, which means g is concave up and concave up. And so here's an example of where our second derivative was 0, a possible point of inflection, but notice that the second derivative did not switch signs there. And also the other thing to notice about this, you might come back and think about, so this was a point which was a place where the second derivative is 0, but yet it didn't switch. What actually was happening there? This is an actual point on the graph. Remember, g was continuous and differentiable, and you should know what x to the fourth looks like. It's essentially a parabola-like graph that comes in like this. So the graph is concave up and decreasing, and then it's concave up and increasing, and yet here you had a second derivative equal to 0. You need to know that that's a point on the graph. So just like we did when we had the extrema where the first derivative was 0 but it was positive and positive, as long as it was a point, you really combine these together. Your answer to this would be g is concave up for negative infinity to infinity because g double prime is greater than or equal to 0. Notice I just put the equals on 0 because that's giving us the adding it in that it was concave up the entire time. We're not going to break it at an extrema like this because that's not a point of inflection, so we're not going to stop. We're just going to do it concave up the whole way. All right, let's take a look back at this next one. Oh, our nice little cube root, which remember we have a cusp alert. Okay, with our cube root, remember that it is a continuous function. F is continuous, but we know that it is not differentiable at x equal to 0, that we had that vertical tangent line there. So let's see what happens when we run our concavity test. Our derivative, again I'm thinking of this as x to the 1/3, so it'd be 1/3 x to the negative 2/3. And our second derivative, again fairly easy, would be negative 2/9 x to the negative 5/3. So we end up with negative 2 over 9 cube root of x to the 5th. So when we look at this, f, the second derivative of x, equal to 0 for no x values. There's no x's in the top. But the second derivative does not exist for x equal to 0. This is still a possible point of inflection. Okay? This is a place where f of 0 existed, f prime of 0 did not exist, but it did not exist because it was a vertical tangent. So that's kind of what we're looking at on this function, is to know what actually happened there. When I do my sign chart for the concavity test, and we put our second derivative and we put our critical value of 0, we will see that in the second derivative, if I pick a number that's negative, overall it's positive, which means f is concave up. And then if I pick a number that's positive, the second derivative is negative, and we end up, oh, sorry, that's not 0 right there. That should be D, N, E. That we get concave down, and we have to do a little bit more investigation. And once we realize that this was a point on the original, but the first derivative did not exist because it was a vertical tangent, we can conclude at x equal to 0, f of x has a point of inflection because f of 0 existed and f of x has a tangent line there. Happens to be a vertical tangent line, which caused my second derivative to not exist. And then we would also answer f is concave up for negative infinity to 0 because the second derivative was positive. F is concave down for 0 to infinity because f is because f double prime is less than 0. Alright, so that's what happens when we have a vertical tangent line. Alright, and we have one more problem to do, H, in this example, a piecewise, because of course we have to look at a piecewise function. So now let's think about this function. We see that it's defined everywhere, and this is okay to have this square root here because when x is negative, a negative times a negative is positive, it will be defined. So our domain is negative infinity to infinity. We might want to think about whether this function is continuous. The only place where it might not be continuous is going to be at x equal to 0. We know that, just because I like to use f, I'm going to call this f of x. We know that f of 0 exists. We know that the limit as x approaches 0, and I'm just doing this in my head, this is not a formal, I'm just trying to figure out what the continuity is, of f of x exists because the left side is going to be 0, the right side is going to be 0, so that limit is going to be 0, and these two are the same, so therefore f of x is continuous. Alright, let's talk about differentiability. So let's go ahead and find the derivative. The derivative of 2x, of x squared would be 2x. That one's easy. X greater than 0. Our derivative, square root of negative x, we think of this as negative x to the 1/2. So the derivative would be 1/2 negative x to the negative 1/2 times negative 1. And we need to check differentiability at x equal to 0. Okay, and remember we're checking that by looking at the limit as x approaches 0 on the derivative to determine our differentiability. If I look at it on the left, it's going to 0. If I look at it on the right, no, we have a problem. So it is not differentiable at x equal to 0. Now we might ask ourselves, what's happening at x equal to 0? Now because the limit of the derivative on this side was 0, but the limit of the derivative on this side, and I'm going to go ahead and just simplify this, this actually ends up being negative 1 over 2 square root of negative x. That the reason that this one, as x goes to 0 from the left, this ends up being a really tiny positive number, which then gets flipped up. So this is actually going to negative infinity and 0. There has to be, this is a vertical tangent on one side and a non-vertical tangent over on the other, and it's just going to be a cusp with a vertical tangent. Kind of a weird graph when you look at it. So it's not differentiable at x equal to 0 because there's a cusp there. Yes, there is also a vertical tangent, but what's more important is that there is a cusp there, so that cannot be a point of inflection. So we're going to go ahead and find our second derivative because we're doing the concavity test. Our second derivative, just using this, is going to be 1/4 negative x to the negative 3/2 times negative 1. Don't forget your chain rule. And once you're out for differentiability, you're out, so 0 is going to be gone. And then 2 for x greater than 0. All right. So our critical values, and again, I might take this one and just rewrite it in a nicer form, negative 1 over 4, your square root of negative x cubed. So our second derivative equals 0 for no x values. Our second derivative does not exist for x equal to 0, but it's fine for all the rest of them. But again, the reason that it does not exist is because we had a cusp on it. Now when I do my sign chart for concavity, I am going to put the 0 on there because that does matter that there's a cusp and a vertical tangent there. And let's see what happens. So our second derivative, if I pick a number that's negative, that's plugging it into this one. If I pick a negative number, that makes this positive, and we have this negative right here, so we end up with a negative number overall. And then after, say I pick 10, 10 would use this version, the 2, that would make it positive. And so we have concave down, and then we have concave up. So this switches, the second derivative switches sign. The original function is switching concavity there, but it is a cusp, so that is not considered a point of inflection. So we would simply say f is concave down for negative infinity to 0 because your second derivative was less than 0. F is concave up for 0 to infinity, and that's because your second derivative was greater than 0. There are no points of inflection because x equal to 0 is a cusp. So that's using the definition of our textbook. Alright, so I'm going to stop this part of the video here, so let you take another break before we do the second derivative test for local extrema.